Hey folks, welcome to Building Recommender Systems with PyTorch. This is a KDD 2020 tutorial led by myself and a number of my colleagues from Facebook. And today we're going to talk about what is PyTorch. My colleague Geeta and I will give everyone an update on the core framework, a number of areas around it, how recommender systems fit in, challenges, solutions, etc. A lot of this is built around DLRM, which is a deep learning recommender model. And so our friends in our AI systems co-design team, Divatsa and Maxim, will be talking about DLRM itself. Narina will be talking about interpretability in recommender systems. And then our friends who lead the multimedia framework, multimodal framework, Manpreet and Vedanuj will talk about using MMF for knowledge-based recommender systems. And we will close with some thoughts and materials and a place where you can actually get all this code and other artifacts from this tutorial. So again, just restating, so some of the folks that are involved, whether it's Maxim, Divatsa, Manpreet, Narina, myself, Joe Spisak, Geeta, as well as Vedanuj. So we are at your service and hope you enjoy this tutorial. But we just wanted to motivate things a little bit. So, recommender systems are really, they kind of fall into this ranking algorithms category. So when we think about search or personalization, it can kind of fall into that kind of general ranking algorithm category. And DLRM is one of the more popular these days. We'll talk about that in a minute. But they're also a little bit different than kind of the traditional deep neural networks that we kind of think, the canonical CNNs, the ConvNets, LSTMs, or transformers. These tend to, these days, be kind of a combination of sparse features, but also, can involve some dense features as well. And again, we'll talk about that. But really, when we talk about these mechanisms, they tend to be these kind of large, sparse, big embedding layers. And they tend to be very difficult to train and expensive from a memory perspective. But overall, what we see is the trend is ideas are getting more complex. I know they are at Facebook. Models are getting more complex. And you can see over time, just in this graph here, how we've kind of seen things. So way back in the day when life was simple, life was very easy. Decision trees were the state of the art. And then things like sparse linear regression, and then everyone discovered deep learning a few years later, and people started using neural nets. And then, of course, we moved on to sparse neural networks. And now we live really in this world of something even more complex. And a great representative model of that is the deep learning recommendation model, as I mentioned, so DLRM. So this is a model composed of both dense and sparse features, and it's purposely built for large-scale recommender systems. It's also a part of MLPerf. So if folks are familiar with the MLPerf organization, and we're on that leadership and have some folks on leading some of the efforts as chairs. So this is kind of your standard recommender system benchmark. And so you can go to the repo in MLPerf on GitHub, and you can see under training, you see the PyTorch sample implementation. And then, of course, you can go to Facebook Research /DLRM, and you can see the canonical implementation there by the team that supports PyTorch. So that's the motivations and intro for the tutorial. So again, really glad to have everyone here, and we're excited to be able to talk about so many really cool areas around this topic. And kicking that off is going to be myself, Joe Spisak. I'm the product lead for PyTorch here at Facebook, and my colleague Geeta Chauhan, who leads our partner engineering effort around AI. So I will move on to into the agenda, and we'll talk about what is PyTorch. So PyTorch fundamentally is, when you look at the mission, it really is about a research prototyping and production deployment. This is really what we ladder all of our goals up to. When we think about how we build community and really harnessing the best of the research world, or building products at scale, everything kind of ladders up to this overall mission of basically enabling researchers to be as expressive and as creative as they can. But there is a portion of that research, whether it's FAIR or other teams at Facebook or other places, that gets into production. So we want to make that kind of flywheel as fast as possible to be able to take research and be able to deploy it at some type of large scale. And the project itself is, of course, an open source project. You can look at it on GitHub. It's under github.com/PyTorch is the core project. We have, I think, actually over 1,400 now contributors. I think closer to 1,500, if I recall. So the project has grown immensely over the last, especially year to 2 years, and the community is really incredible. And when you actually drill down into PyTorch, like, what is it? I think that, I think for this audience, probably this isn't as germane because these are, really experts in the field. But when you actually drill down to it, it's actually really a set of libraries and functions and tools and other things that you can basically use to develop neural networks. So it could be, for example, torch.nn, which is really just the your canonical way to define a layer. Or your optimizer, or how do you load data sets. So there's a bunch of utilities we have for loading data. There is the AutoGrad set of APIs, which provides the auto differentiation. So this is what this is all the magic behind when you call loss.backwards. There is a set of domain libraries like Torch Vision, which provide models, data, transforms, etc. And then, of course, really the beating heart of how we actually ship models in production in torch.jit in our just-in-time compiler, and the associated language that we use to do that, called Torch script, which is really a Pythonic DSL, a domain-specific language that basically does not have a global interpreter lock, and that can be essentially shipped in a Python-free environment. So I want to talk at least a bit on the principles of the project. So, we've kind of seen the overall mission, but how do we invest, or what do we invest in? What do we think about when we invest in features around PyTorch? So there's quite a few here, but I would say these kind of hit some of the higher order things that we think about. So, we always think about eager and graph-based execution. So we know we need eager mode. We know that we want researchers to be free to explore in this kind of Pythonic, defined by run type of environment. But we know we need to get into a graph at some point when you want to move into some type of scale. We also know that the world is more dynamic these days. We've seen this the last few years with control flow and variable length, data, and really just this isn't a feed forward static world. Things are very dynamic, and we want PyTorch to be able to enable that. We've also noticed, of course, that models are getting larger. So if you look at GPT-3 at 150 billion parameters, and even pushing beyond that with some of the more recent models, distributed training, especially model parallel distributed training, is becoming more and more important as these models just don't fit into memory anymore. So that's an area of investment. Fourthly, hardware acceleration. So whether it's cloud TPUs, better support for NVIDIA GPUs, or the myriad of other hardware accelerators and devices that are out there, either in servers or in like on device, like phones or otherwise. This trend is not going away, and so building clean abstractions and clean integration points to support a diversity of hardware is important. And then generally, when we think about new APIs, we think about simplicity over complexity. So, there's typically one way to do something. We try and give as much thought as possible and talk to users, look at their pain points, look at usability, and think about usability whenever we introduce a new API. And I think this has really paid off for us as a project. And so when we think about really developer experience, if I drill down in that for just a second here, there's three things that we think about. One is really that full freedom to iterate and explore, like, whatever you're doing, whether you're trying to work in reinforcement learning and in robotics as an example, or scientific type computing with some of the newer APIs that we have. It's important to give users the kind of that full freedom. Second, again, clean and intuitive APIs. It should be very, very easy to understand, like which APIs to use, when to use them, and why you're using them. And then thirdly, PyTorch is a core. It's one piece of the puzzle, but there are other things around it. So having a set of tools and libraries that accelerate you as a developer, so whether it's like visualization, whether it's deployment, whether it's full lifecycle management, ML ops, etc. There's a really rich ecosystem around PyTorch that provides a lot of this in the way of capabilities. So one thing I wanted to just get concrete with code for a second here, to give everyone just an understanding of how this actually manifests within the project. So if you look on the left here, this is again a very simple model, a couple of fully connected layers, and basically we are using the Torch NN module subclass here. So basically we're using nn.linear to provide our linear fully connected layers. And then we define a forward method, which basically provides, the nonlinear functions and activations that are required, as well as your, regularization with dropout. And so it's pretty intuitive, I would say, in how you do this. But this actually isn't really the important point of the slide. The important point is really when you think about how we've also defined like our C++ API, which looks eerily similar, and that was of course by design. So we wanted basically to have this intuitive API, and whether you're developing in C++, maybe you're doing reinforcement learning for something like high performance gaming, maybe you're doing something around like AlphaGo or OpenGo, like we did in our FAIR team, where they use the C++ API, or you just want to more seamlessly integrate your model into a C++ application. You don't really have to learn a new syntax, and it really does allow you to kind of flow back and forth between the two APIs. And you can see, as I've defined the net, so net equals net, I load my data using, say in this case, like Torch Vision, which provides a really nice abstraction for data sets, especially the vision data sets here. And I'm loading MNIST with a couple lines of code. Define my optimizer, and then my training loop. And of course, if you don't want to write a training loop, you can always use one of the fancy libraries like Ignite or PyTorch Lightning, which provides you a much more simple API. I think more researchers and folks doing more exploration like to have a little more control over training loop. It's up to you as the user, whatever you want to do. In this case, we're running running a few epochs here, 1 to 11, and zeroing out our gradients before we actually run this thing as a good practice. Running it forward, defining our loss using negative log likelihood, and then basically doing a loss dot backwards, which does a back propagation, and then taking a step, and then doing a checkpoint afterwards. So very simple. And again, you can look at the C++ and implementation as well, and it matches almost to the line. It's pretty cool. I mentioned tools and libraries. So this is only a handful of some of the ones that they developed. If you go to pytorch.org/ecosystem, there's a number of projects, literally dozens of projects that we review, and then we'll put on the page, and these are projects that have a great user experience. They have great documentation. They have support in place. People are supporting these kind of longer term. But you can see, for example, some of the things like PyTorch 3D or Crypt10, for encrypted AI, or Captum for interpretability. These are fantastic libraries that will help developers kind of fill out the end-to-end platform or help you explore different areas, like, for example, private AI or privacy-preserving machine learning. So switching gears, I want to talk about the community. So again, this is such an awesome community, and one of the reasons that I personally am involved with this project, and what gets me excited about really working within this community. And so when you look at some of the folks that are in there, whether it's Jeremy Howard or Ander Karpathy, our friends at Google who we launched Cloud TPUs last year with together. It's such an amazing and organic community that has kind of grown up around the project. We've also seen some players and others kind of join the party with us as well. While the project has a broad set of contributors and distributed ownership around the code, a number of companies have also recently joined us, and you can see like O'Reilly comments around researchers and articles about how researchers are loving it, but also Preferred Networks in Japan made an announcement, and they're all in on PyTorch and moving away from Chainer, which had a great community over in Japan. And also OpenAI has recently joined in January, and they're building all of their research on PyTorch. So that's super exciting. So numbers, just a quick set of metrics here. I mentioned like we're close to 1,500 contributors. Now that's actually well over 50% year-over-year growth. So the community just keeps growing quickly. We also don't tend to use Stack Overflow for issues. We have a discussion forum. So if you go to discuss.pytorch.org, we have over 32,000 forum users with hundreds of thousands of questions and answers and comments. So there's this just vibrant community of users out there that are active and answering each other's questions and supporting each other, and so on. And then, one of the really interesting sites that's out there is paperswithcode.com. If you go to paperswithcode.com/trends, there's this kind of interactive chart that you can play with, especially if you're into frameworks and into developer tools. This is actually really interesting. It kind of shows over time how many repos have been created based on paper implementations by framework. And you can see PyTorch in red, so we're doing pretty well if you look at the graph, which is really exciting for us. Okay, I'm going to shift over to some of the things that PyTorch is, as a project, is focused on, and this kind of aligns with some of the challenges that we see in AI ML and some of the just overall trends that are happening in the space. So I think everyone has seen a variant of this graph, and this is of course out of date because of GPT-3, and as well as the model that Google released that's in the hundreds of billions of parameters as well, the mixture of experts paper. So this chart does get out of date very quickly, but the point remains, parameter counts are continuing to grow. This seems to be a trend that just won't go away. And one of the things that's a challenge here is that actually deploying these models at any kind of reasonable scale isn't really tractable. So even BlenderBot, which is a model that Facebook open sourced a few months back, is around 10 billion. I think there's a version that's like 11 billion, and it's very hard to deploy. This trend continues, and and these models just keep getting larger, and it's very difficult to deploy them. As I mentioned with BlenderBot, at 10 billion, close to 10 billion parameters, it required several V100 GPUs to even run any kind of inference for the model, which is pretty incredible. So one thing that we've seen is really this this rise of model optimization, and whether it's techniques like distillation or pruning or quantization, but the general ability to remove parameters, and prune these parameters, remove these parameters, or run these models in some type of lower precision is a trend that's been around for a while, but it's even more important now. So if you look at pruning, this is an area where you have these models that have just this over parameterized models or hundreds of billions potentially. And so how do you optimize that model? How do you compress that model down by reducing the number of parameters without sacrificing accuracy? That's a fundamental premise of pruning. And so we have an API there, and we have a nice tutorial on PyTorch.org that walks you through that. And Michaela Paganini worked really hard on this library, and it came out great. And that's available. Also, quantization. I mentioned like really, neural nets historically have not been sensitive to precision. That's why we don't really care about things like IEEE 754 compliance or double precision or so. This is actually an opportunity for for us to actually reduce the precision of our computations and be able to run them on hardware that actually supports basically lower precision, so something like maybe integer 8 type computations. And so, for example, this could be IoT devices or mobile devices, but it could also be servers running an inference at scale. And you can see on the right here, there's an API example, very simple one, taking ResNet 50 that we've actually pre-trained as part of, like, say, Torch Vision, and basically running some level of quantization based on a Q config, which I kind of hid the complexity here a bit, but you will configure basically how you want to quantize it, what layers, as well as what precision, and then be able to basically convert that model into something that can run at a lower precision. And so, what is the result? I mean, the result is pretty good. We've been using it at Facebook for a number of years now. It's never been really nicely integrated into a framework, but we're getting that now into PyTorch, and which really allows us to democratize it across the company, and as well as externally in the community. We're starting to see great adoption of quantized models. And so, concretely with something like ResNet 50, which is a pretty popular model and used in benchmarks and used for a lot of classification tasks for computer vision, we've seen basically a 2x performance speed up with basically, marginal loss of accuracy. And same with MobileNet V2, which is a model that was built, kind of purpose built for mobile applications. We saw actually even better speed up using quantization aware training in 4x. And with NLP models, we looked at, for example, translation using FairSeq, and Blue Score is basically a metric for accuracy in translation. We were able to use dynamic quantization in this case, so basically quantizing the weights only, and we saw also a 4x speed up using Intel Skylake. So really incredible, and this can really allow you to scale on either mobile devices or servers and build efficiency. The other challenge that we see is training models at scale. So, when we think about the challenge here of, things are expensive and experimental. In other words, like, ML jobs are not like normal jobs. They're not like building a data pipeline, right? They tend to be ad hoc. We may do some checkpointing and we may run a number of them depending on the number of hyperparameters we want to run, and some of them may die, some of them keep going. So in short, these are jobs that are basically atypical compared to what is kind of standard in infrastructure. And so the fundamental thing is it actually makes it hard to do like demand prediction and control. Like, how do I predict the number of jobs and training jobs that basically my researchers are going to be deploying, because they don't know, and research is a very unpredictable area. And so as a result, basically cost and efficiency is a very difficult thing to get your mind around. How do you actually justify the ROI for spinning up maybe 1,000 GPUs and basically occupying that compute for some period of time, when maybe actually you may not actually get a model that is high quality enough out of that training job. So anyway, so ROI ends up being very difficult, but also just generally, like, you have all this expensive compute. You have servers, you have GPUs and CPUs, you have infrastructure around it with networking and power. And when you're operating in this kind of sublinear environment, plus when you talk about the scale that, say, companies like Facebook operate or others, it's very, very easy to waste resources. And this could be millions of dollars and a lot of power and cost. So one of the things that we thought about is, how do we do this in really this elastic, fault tolerant way? And so Torch Elastic was our solution to this, and it's really getting pretty incredible adoption organically across the community. And this is things like being fault tolerant. So if you're running, for example, in a cloud environment, this is basically a non-HPC cluster. So if you're in a supercomputer and everything is basically kind of captive audience, I have dedicated servers, great. I can probably run without some level of fault tolerance. But if I'm in a cloud and maybe I have preemptible instances, like as AWS calls them, spot instances, like this actually is much more difficult. I may also have mission critical production jobs that I want to be able to run, and I want to make sure that it doesn't fail after a certain period of time. Some of these jobs can last for days or weeks, or even months. Also, when we think about these spot instances, that like, how do I actually dynamically change and auto scale based on like the availability? So if those nodes go down, but then they come back up, I want to be able to take advantage of that compute and be able to accelerate my job when that compute becomes more available. So that's kind of the premise of Torch Elastic. But what if my models are really big, right? If I'm running at really, really big scale. So this could be, for example, tens of billions of training examples. This could be, as I mentioned previously, models that are larger than the machine itself, larger than, say, the GPU memory or even the CPU memory. What if I'm running, say, hundreds of experimental runs and they're competing for resources? What if I have 1,000+ different production models? Like this is what we mean about production or really large scale. So one of the things we built is this PyTorch RPC framework. And RPC stands for Remote Procedural Call. And what this does is actually enables applications to run functions remotely and automatically handles things like autograd. So in other words, if I'm running on all these different devices and I'm running maybe some layers over here, if I'm running layers over there, or I'm splitting my model in different ways, but how do I handle this, the auto differentiation, just as an example? And that's what PyTorch RPC handles for you. And I'll get into a little more detail in the next slide. But first and foremost, what this does is it allows you to handle these types of, say, parameter server type approaches, or if I have, for example, reinforcement learning use cases where I say I have multiple observers streaming states and rewards to the agent, and I'm doing this kind of policy training. Or I could also be doing, say, distributed model parallel, which is great for these large sparse NN type models, which is kind of why we're here today. We're talking about DLRM. And of course, the hog wild training, which is, believe it or not, still used today. So just a quick primer on RPC. So there's really 4 things to keep in mind here. And again, this came out in PyTorch 1.4, which is earlier this year in January. There is the RPC portion, which is really the user code with arguments and some specified destination location. There is the remote reference, which basically tracks and maintains objects owned by the remote workers. And then there's distributed autograd. So one of the things that's historically painful is, how do I actually connect all these graphs and actually do back propagation through the graph when they're distributed over a bunch of workers. So building an abstraction that basically allows you to connect all those graphs from those different workers into this global graph, and then basically give you something similar to lost off backwards and make it as easy as possible for the user. As well as a distributed optimizer. So similar thing, you have an optimizer. How do I deal with that? The fact that I need to run, like SGD across all of these different remote workers. Okay, I'm going to switch gears and talk about deployment at scale. So this is one of the other challenges that we've seen in the PyTorch community. So, I think we've been deploying models for quite some time at Facebook. DLRM is a really interesting model. It's a very compute heavy model, but also it hits the memory bandwidth quite hard, as you'll find from Divatsa and Maxim's talk later on. But all told, some of the things that we've seen is really, there's a number of pain points of just deploying models. I think everyone likes to train models and talk about authoring new models, but being able to deploy them at scale is actually pretty difficult. And some of the things we've seen is being able to just load and manage multiple models. How do I have multiple models on multiple servers? Maybe in multiple clouds or multiple type devices. How do I handle like running pre-processing and post-processing code around the prediction requests and be able to do that pretty, in a straightforward manner? How do I log, monitor? How do I secure predictions and have a way to ensure that my model can't be hacked when it's doing predictions? And of course, what happens when you hit scale? And so one of the things we worked on with the Amazon folks, AWS, is Torch Serve. Torch Serve is essentially a model server, provides a set of APIs for inference as well as management. It has a default set of handlers. So basically, if you're doing things like text classification or image segmentation, you can also do custom handlers. There's also the ability to version your models, roll back to earlier versions, do auto batching across HTTP requests, all of the usual like logging and metrics, as well as I mentioned previously, a robust set of APIs accessible through HTTP for both management of your models, but also to handle how inference is performed. And that is open source. If you go to the PyTorch org and GitHub /serve, you can find that repo. Okay, lastly, I wanted to give everyone an update on the latest for PyTorch and the release that we have that came out fairly recently, as well as some ways to get started. Okay, so PyTorch 1.6 released the end of July. So this is, we tend to do releases roughly every quarter, and then so every 3 months or so, with maybe a maintenance release in the middle, depending on if we accumulate enough issues to warrant one. This was a really, really good release. It had some nice and interesting features that are really valuable. So first and foremost, we added automatic mixed precision training. And this basically allows you to take advantage of some of the great features that NVIDIA has in their GPUs around, say, like float 16, and be able to basically automatically decide which layers in your network require higher precision and which ones require or can tolerate lower precision. And this is a very clean API. It's very simple to enable in your model. And it can basically speed up your models, sometimes orders of magnitude, and reduce memory consumption. It's pretty significantly as well because of the ability to use lower precision, like I said, like FP16. We've also added something called TensorPipe, which is basically a tensor-aware point-to-point communication set of primitives. And what this does is, in addition to the collectives that we support in distributed in our backends for distributed training, we also now support a point-to-point backend, and this is what we're calling TensorPipe. And then thirdly, we added profiling tools. So one of the biggest things that biggest features we've been asked for is the ability to do tensor level memory consumption and be able to understand how we're doing across CPUs and GPUs. And so that's supported now as part of the AutoGrad API. And then fourthly, we've had just a number of overall improvements for distributed data parallel training as well as the RPC packages. But what's interesting is actually we've implemented the ability to actually mix and match dense and sparse type of training. So basically, you can mix DDP and RPC now pretty seamlessly, and there's a new API that supports that. In addition to the core framework, we released a number of domain libraries that we've added new features to. So for those who don't know, you should know, we have really three main ones that we maintain, and we are considering more in the future. but one around vision, so computer vision, Torch text for NLP, and so on, as well as Torch audio. And so Torch vision, we've added some new models for semantic segmentation. So you can see, the FCN based on ResNet 50, DeepLab v3, which is also based on ResNet 50, and both trained on the COCO dataset. We've also added AMP support in Torch Vision, which is really cool. So you can basically do autocasting for models and operators in Torch Vision. In Torch Text 0.7, so we basically are revising the dataset API to basically be compatible with PyTorch's data loader and sampler, and added some nice pre-processing defaults as part of that. And so the revamp of Torch Text continues, and we made a big step forward in this release. We've also added a new multi-head attention module that you can basically have a high level of customization within. Windows is now supported. We've been Linux only for a long time on Torch Text. We've also added Torch script support for sentence piece models, so it allows you to ship those into production. And we've also added a pre-trained BERT example pipeline, for a question answering type use case, along with 2 Q&A data sets. Lastly, Torch audio, again, Windows is added as well, so that's great. We have Windows across the board. And then we've also added a number of new things. So we've added new models like wave to letter. We've added some new functions. You can see all of the new audio functions that we have, data sets, as well as SOX backend support for Torch script is actually available, but optional if you want to use it. So how do you get started? Where are all the docs, where are all the tutorials, where are all the blog posts, etc. If you go to pytorch.org, you can always click on getting started. We have a nice handy little selector, select your version, select your OS, select your package management. If you want to use pip or conda, etc. It's all supported there. If you want to do any kind of any other learnings, if you go to Udacity, most of their classes are built on PyTorch. We have, of course, an intro to deep learning PyTorch course that's free. There are a number of other courses. There are computer vision nanodegree, privacy and AI. All of that is built on PyTorch, which is really awesome and really useful. There's also a number of books. So I'm just kind of showing a couple here, but whether it's Dilip Rao's Natural Language Processing with PyTorch that came out last year, or Eli and Luca's book on deep learning with PyTorch. And if you go to pytorch.org, it's actually free. You can download the PDF with basically a very simple form. I think they ask you your name and what you're going to build with PyTorch, and that's about it. I'm not even sure they asked your name, but it's a very simple form, and you can get a really nice book for free. And it is a fantastic book. I was a reviewer on it, as were a number of the PyTorch core devs. And Fast.ai is also a great resource, and Jeremy's book, his new book, is coming out in about a month or so here. At the time of this recording, it was about a month out. I think it's in August, early August, that it comes out. And that'll be on Amazon through O'Reilly, so I would definitely check that out. And of course, his MOOCs that he puts out. We also have docs in Chinese. So if you go to pytorch.apachecn.org, you can see a lot of the docs and tutorials in Chinese, which is nice. And then we have a fantastic community in Korea, and they've done a great job of basically translating pretty much everything over into Korean, and that's pytorch.kr. And if you want to follow us and keep in touch and learn about what we're up to, we're on pytorch.org, we're on Twitter, we're on YouTube with lots of great videos. Of course, we're on Facebook. And one of the things that's really interesting is our medium.com/PyTorch channel. I think we posted something like close to 40 blogs in the last month or so, with most of those from the community around new libraries, new tools, all kinds of new information, and kind of great walkthroughs to get you started in a number of areas. So I would definitely go to that Medium channel, subscribe to it, and read some of the blogs. They're really useful. Okay, I'm going to pass it off to my colleague Gita to take us home on PyTorch on the PyTorch section, talked about recommender systems, the state of the world, what are the challenges are, what the solutions are, and I'll hand it off to her. Thank you, Geeta.
Thanks, Joe. My name is Geeta Chauhan. I lead the AI PyTorch Partner Engineering Group at Facebook. I will now go into details of recommender systems, their unique challenges, and the current state of the art for building recommender solutions. At Facebook, we use recommender systems for many of our services, like the newsfeed ranking, the stories ranking, and the Instagram Explore. At Facebook, recommender models comprise of almost 50% of all our AI training cycles and 80% of AI inference cycles in our compute clusters. Meanwhile, if we look at the research community, the papers published in top systems conferences in the past 4 years, things look much different. So there is a big disconnect between the areas where the researchers are focusing and what is needed by the industry. In order to understand the problems, let's start by looking at what recommender systems do at a high level. At Facebook's scale, we are dealing with hundreds and thousands of items, and we have to decide how to rank these in order to make a prediction to show something to the user. So we start off with these candidate items and pass them through the recommendation models that have billions of parameters and get a ranked list which goes out to the users. On top of that, the scale of Facebook's users is in billions. So you have an enormous number of these predictions happening at data center scale in parallel. Diving into how recommender systems work from an algorithmic standpoint, we see that there are a set of continuous dense features like the age and time of day, and a set of categorical sparse features like the user's search history and the pages she visited and the book's genre. The dense features represent questions for which there is a concrete answer. And the sparse features are for range of yes and no type of questions which are related to the user or for the items being recommended. Now these sparse features are encoded into embedding tables which are then integrated with the dense features to get to a prediction with percentage score for each of the items. And finally, we create a ranked list of recommendations of what a user may like. When it comes to evaluating the recommender models, there are a couple of things we need to keep in mind. First of all, it is widely known that ranking more items leads to better recommendations. So from a system standpoint, we focus on high throughput to evaluate lots of different candidate solutions all at once. And since we have a user waiting at the other end, we have a firm latency requirement. Otherwise, the user will abandon the site and go somewhere else. So what this means is that from an optimization point of view, we focus on latency bounded throughput for the recommendations. This poses some unique challenges for building recommender systems, and they fall under three main categories: the embedding tables, the model heterogeneity, and the performance variance. Embedding tables are an order of magnitude larger compared to the CNN, RNN, and fully connected models. However, when we look at the compute intensity side, their requirements are much lower, so they need fewer flops per bytes. Due to the sparse nature of the data, the memory access pattern is very irregular, however, and this poses additional challenges. Within the recommender systems themselves, there is a wide diversity. So if we look at three key recommender models at Facebook, they all have different attributes. So different fully connected sizes, different number of embedding tables based on the task and the data domain. The size of the embedding varies. The number of lookups per table also varies. And if you start to look at the bottlenecks that get introduced by each of the models and try to hone in on specific operators where all the time is being spent, that too varies widely across the models. So you can't optimize for any one operator that is generic for all recommender models. The sensitivity of the models on how they would perform on underlying systems also varies. So if we take an example, for the models are very sensitive to the configs like the batch sizes and its impact on specific systems. As a result, one need to co-design the models with the actual hardware on which they get deployed to get an optimal performance. Now let's look at the state of the art for building recommender systems. The solutions fall under three main categories. Personalization, API-based solutions like AWS Personalize, the frameworks and libraries like the Microsoft Recommender Library and the NVIDIA Merlin framework, models and benchmarks like the Facebook DLRM model and the MLPerf industry benchmark for machine learning training and inference. Another key ingredient that was missing for the recommender space for a long while was a good open set of datasets. And the Criteo ads dataset closed this gap and now opens up doors for the research community to experiment and build new models similar to what happened for the CNN and the RNN space. So let's hone into a couple of these. So here is an example of AWS Personalize, which is based on AutoML. In this case, the domain experts upload their data and tune a few parameters. For example, they identify the features, select the algorithms, select the hyperparameters, based on which a custom model and an API is generated. The NVIDIA Merlin framework is specifically designed for recommender systems. It has the NV tabular for optimized data loading, the huge CTR for training, and Triton as the inference server. Microsoft's recommender library comes with a wide range of pre-built recommender models and predefined datasets, including the Criteo dataset. Facebook's DLRM is now part of the MLPerf benchmark, and the best part of the solution is that it is fully configurable. So you can tune how many dense features you want, what is their size, same thing with these sparse features, different layers, all that is tunable, based on which you can do your research, run your research experiments on different platforms and get an optimal solution for your particular needs. So let's dive into some of the research tools for recommenders. We just talked about the DLRM, which is part of the MLPerf benchmark now, along with the Criteo ads dataset, which includes both the Kaggle dataset as well as the full 1 terabyte dataset. We are also working with our ecosystem partners for optimized models and workflows. So for example, with NVIDIA, we have an optimized version of DLRM, which just got launched on the Ampere GPUs and has support for fast data loading with Spark on GPUs. And new distributed version of DLRM heterogeneous data parallel and model parallel version. The Intel optimized DLRM using their bfloat 16 solution. We are also working with Google for DLRM on TPUs, and reference architectures for Azure and AWS are also coming out soon. On Papers with Code, you can find the state-of-the-art models and papers with actual code, which can give you a jump start for your research. Finally, with the PyTorch 1.6 release, we added support for building heterogeneous DDP and RPC models. So you can now use DDP for your dense features and DMP for your sparse features where your embedding tables do not fit into a single machine. So I hope I got the message across on the importance of recommender systems. They are underinvested, have unique system challenges, and now with the benchmarks and data sets, doors have been opened for you all to innovate and do novel research for new types of systems of the future. I would like to leave you with few references. And in the next section of the tutorial, Maxim and Dhivatsa will dive deeper into DLRM. Thank you very much.